Right, so in this lecture, we are going to talk about finite element equations and the direct stiffness method. Now, we're going to keep it fairly light in this lecture, and all I really want to do is establish a couple of different ideas and really just set the scene, set the roadmap for what it is we're going to be doing in this section and why we're going to be doing it. So, we're going to start off making a couple of notes, and the first one is that the finite element, right, or FE for short, finite element equations are used to calculate the element stiffness matrices. Okay, right. So again, we're doing a course on the finite element method, and in particular the direct stiffness method, and I'm going to define those two terms in a little bit more detail now shortly. But essentially, as I've said already, this involves modeling the behavior of structural elements, and in order to do that we need to work out element stiffness matrices. Now I'm going to again explain that in a little bit more detail now shortly as well. So in order for us to do that, in order for us rather to get these element stiffness matrices, now we can derive them directly, so to speak, and we're going to see an example of that here, which works very, very well. We can derive the element stiffness matrix for a bar element very straightforward, very easy. But when it comes to more complex elements, structural elements, for example, beams or 2D elements, we're going to rely more on finite element equations. Now, as it turns out in this particular course, we're only going to be focusing on axially loaded bar elements in order that you can model truss structures. But the likelihood is you'll probably, when you finish this course, you'll probably go on and take the subsequent degree tutors course on applying these methods to beam structures or beam elements. And when we go and do that, we're definitely going to want to rely on the finite element equations in order for us to do that. So it might seem like a little bit overkill for now, for what we're going to be doing in this course. But as I said, you're probably not going to stop here. You're going to go on and do some further study on the direct stiffness method, in which case you're going to want to know this sort of fundamental foundational material. Right, so that is the finite element equations. Now, I've also mentioned this term, the direct stiffness method, right? The direct stiffness method describes a process of combining element stiffness matrices together to form the structure stiffness matrix. And once we have a structure stiffness matrix, we can solve that to find nodal displacements. Now, don't worry if all that seems a little bit unclear, a little bit abstract at this point. We're gonna step our way towards it, so it'll make much more sense. But in short, what I'm trying to get clear in your mind here is these two different terms, right? We've said the finite element equations, and they allow us to get the stiffness matrices. The direct stiffness method then is a method that combines element stiffness matrices together, and once we do that, we can form a structure stiffness matrix, and a whole analysis process flows from that. Now, we've also mentioned this term, the finite element method. The finite element method is just it's a sort of a broader term that describes any structural analysis procedure where you're evaluating the behavior of individual elements in order to bring those together to form an overall structural model. So the direct stiffness method is a finite element method, right? The direct stiffness method is a more, what would you say? It's a more refined, specific name for what we'll be doing, whereas the finite element method is a more general term, which also applies to what we'll be doing. So to a certain extent, finite element method and direct stiffness method, to a certain extent, they're kind of interchangeable terms, okay? And we'll just write a couple of quick notes on what I've said there. So we'll start off with the first note that says the finite element equations are used to calculate element stiffness matrices. And the next note we want to say, or write, is that the direct stiffness method describes a process of combining element stiffness matrices together to form what's called a structure stiffness matrix. So in this section of the course, not necessarily all in this lecture, but in this section of the course, we're going to determine these finite element equations, and we're going to use these equations to determine the stiffness matrix for an axially loaded bar. Right, so it would be helpful at this point, I suppose, to have a bit more of a clear idea of what this element stiffness matrix is, because I keep mentioning it, but it mightn't be obvious to you or clear to you yet what that is. So that's what we're going to have a look at now. So let's think about, let's just set up a little heading here of the element stiffness matrix. We'll start off by thinking about a spring, right? So as usual, let's start off with the simplest model we can think of, right? So we've got a little spring here. Okay, and now we're going to think about what happens when we apply a force to the end of that spring. So we've got the same magnitude force applied to each end, so spring's in equilibrium. The spring is characterized by a stiffness, right? So that spring has a stiffness, and we often refer to that with the letter K. So that's going to be the stiffness of the spring, and that will have units of force per distance. So I'm going to choose newtons per meter. Now, when I apply a force to that spring, what happens? Well, I'm going to see that the spring gets longer. Let's say this end here is stationary, right? So all of the extension is located at the other end here, right? So I'm going to get a deflection. I'm going to call that deflection delta. Okay, so far so good. We can all conceptualize and imagine a spring. So the spring has a stiffness. Now, we are hopefully familiar with Hooke's law. If we're not, that's not a problem because it's pretty straightforward. Hooke's law, what does that say? That simply says that the force in that spring, F, is equal to the stiffness times the displacement. Okay, so what are we saying here then? We're saying that K is the constant of proportionality between force and displacement. So we've seen this idea before, this constant of proportionality. We have it between stress and strain, and it is Young's modulus. And for force and displacement here, in the simplest case of a spring, that constant of proportionality is the spring's stiffness. Let's write a quick note on that then. Now, in the same way that the constant of proportionality between stress and strain, Young's modulus, in the same way that that expanded from being a single constant in uniaxial stress, that expanded into a matrix. Well, the exact same thing happens here for a bar element, right? When we're considering a bar element with forces on each end of the bar, that constant of proportionality between force and displacement expands into a matrix, okay, and that is the stiffness matrix for that element, right? So let's think about that for a second. We've conceptualized a spring here, and we can kind of understand intuitively what's happening here. Now, if I expand that to think about a bar element, so exact same concept, but we're just saying expand to consider a bar. Now, the stiffness of a bar is actually EA over L, Young's modulus, times the cross-sectional area of that bar over the length of the bar. Okay, and if we just look at the units of that, we evaluate the units, we're going to have, let's say, Young's modulus has the same units as stress. So let's just say newtons over meters squared. Area obviously has units of area squared or length squared, which is, we're going to say meter squared in this case. And that all gets divided by the length, which has, we're going to say units of meters. So they would cancel out, and we'd end up with a stiffness with units of force per distance or newtons per meter, which corresponds to what we had when we were looking at the units of stiffness here, okay, for a spring. So this is the stiffness of a bar element. So now we need to generalize this force displacement relationship for the case where we have potentially two different displacements at either end of a bar. So we'll just say we're going to generalize to allow for different displacements at both ends. Okay, so we can start off here and sketch out our bar element. Okay, so we've got a bar here with node 1 and node 2, and we've set up an XY axis system. So what we have here potentially is a situation where node 1 could have displacement delta x1 and node 2 could have displacement delta x2, because remember, this bar we're assuming is part of a larger structure. It's an element within a larger structure, and as a result of that, because there's likely to be other members joining at node 1 and other members joining at node 2, we're likely to have different displacement magnitudes at each end. Okay, now corresponding to displacements, we're going to have a force develop at each end of the bar as well. So we'll call this Fx1 and Fx2. Okay, so we have a force developing at each end, and correspondingly we have a displacement developing at each end as well. So now what we want to do is relate the forces to the corresponding displacements. That's essentially the nature of the stiffness matrix. It relates the actions at the nodes of an element to the corresponding displacements or rotations in the case of moments. But for the time being, we're just focusing here on forces. So we'll say we're going to relate the forces to the displacements. All right, so let's think about fx1 here, right? So fx1 is going to be equal to the stiffness times displacement. Remember, that's the fundamental force displacement relationship. Force equals stiffness times displacement. Now, for our axially loaded bar, that's going to be A over L for the stiffness times the displacement. Now, the displacement is going to be delta x1 minus delta x2, because we need to remove, we're essentially removing or subtracting the influence of the displacement at the other end. And similarly, we can say that fx2 is again EA over L times, in this case, delta x2 minus delta x1, because again, we're removing that displacement at the other end of the bar. So each of those equations can essentially be expanded. They can be expanded. So we can end up with fx1 is equal to EA over L times delta x1 minus EA over L times delta x2. And similarly, fx2 is equal to, if I just rearrange slightly, minus EA over L times delta x1 plus EA over L times delta x2. So hopefully you can see where I'm going with this. This is more easily or more readily or more conveniently represented in matrix form. These two equations, we can represent them in matrix form, and from that we're going to be able to identify or extract out the stiffness matrix. So what we can say is just taking these guys over here, these equations over here, and representing them as a matrix or a matrix set of equations, we would have the vector of nodal forces is equal to a square matrix EA over L, 1, minus 1, minus 1, and 1, times the vector of axial displacements at each node, delta x1 and delta x2. Okay, excellent. And what we're saying here is that this guy in the middle, this square matrix here, is our local bar stiffness matrix. And look at what it's doing. It's relating the forces at each end of our member here to the corresponding displacements at each end of the member. Okay, so let's just get a quick note on that. So we'll say this square matrix in the center here is the local bar stiffness matrix. And it relates the unit end forces to the unit end displacements. So if we were to just multiply that EA over L through, we would end up with in a matrix. Well, you've probably seen that version of the stiffness matrix, but you'll also probably have seen this where the EA over L is multiplied through. Okay, so again, that is just another representation of the stiffness matrix. And just to say that these guys, all of these individual elements here, these are our stiffness coefficients. All right then, so that is essentially how we identify or how we extract the stiffness matrix for an axially loaded bar. And remember, it's a very simple concept. It's a simple idea. It's just relating the forces at the ends of a bar to the corresponding displacements. Okay, so let's just think about this for a second at a slightly higher level. Let's just create a little bit of space for ourselves here. Right, so what have we got? We've got two displacements, right? We come back to our bar here. We've got two displacements, delta x1 and delta x2. And as I said, this bar is usually part of a larger structure. And there's other elements connecting to node 1 and there's other elements connecting to node 2. Now, as a result, when load comes onto the overall structure, you're typically going to have different values of delta x1 and delta x2, right? So, delta x1 and delta x2 will be different magnitudes, and as a result, the bar is either going to get longer or shorter. So let's just get a couple of notes down here just to clarify our thinking on this. So we're saying that delta x1 and delta x2 are typically different. And what that means is there's going to be a lengthening or shortening. So we'll just say, therefore, bar gets longer or shorter. So we'll just call that the change in length, delta L, right? So obviously it's the degree to which the bar gets longer or shorter that determines the magnitude of the force. Or you can think about it another way, it's the magnitude of the force that leads to the change in length of the member itself. Now, one important observation that we can make based on this stiffness matrix is that fx1 and fx2 are going to have an equal magnitude and they're going to be opposite in direction. Okay, and we know this is the case, and we know this must be the case because the bar itself must be in a state of static equilibrium. So to demonstrate that, to make that point really clear, let's just have a think about a bar, an example, a short numerical example of a bar here. Let's imagine we had the same bar. So this bar here, and let's imagine let's imagine delta x1 was equal to, let's say, 2 millimeters. And let's imagine delta x2 was equal to, 5 millimeters, right? Now, if the right-hand side of the bar is moving 5 millimeters and the left-hand side is moving 2 millimeters, well, that means the bar must be getting longer, right? There's a change in length, an increase in length in the bar, right? And so if we were to use that in our force displacement, we would say F is equal to EA over L. So it's easier to just think about it in the context of the equation in that form and then the equation in that form. But essentially what we're saying here is that F1, the force at Fx1 is EA over L. Now we said delta 1 minus delta 2. So that's going to be delta 1 was 2, delta 2 was 5, so it's 2 minus 5 is going to give me a minus 3. And if we were to do the same thing for the other end, we'd say fx2 is equal to EA over L. And this time it was minus delta 1. So that was going to be minus 2 plus 5, which would give me 3. Okay, so again, well, we're saying 3 EA over L and 3 EA over L. Okay, so we can think of it, what does that actually mean? So for our bar, let's just draw it here. We said that the force Fx1 was in the negative direction. So notice that the magnitudes, the absolute values of these forces are both the same. So that's good. Okay, so we can say the magnitude of Fx1 is equal to the magnitude of Fx2, okay, which makes sense to us. And we also note from the signs of the forces that the force at x1 is going to the left, and that's going to be, well, let's just call it 3 EA over L. And the force Fx2 is going to the right, and so it was positive, so it was going to the right, and that was going to be, again, 3 EA over L. All right, and that makes sense to us. We know that that bar is getting longer, and it makes sense to us, therefore, that the forces applied at each end of the bar are tension forces pulling that bar and increasing its length. Okay, so that's really all coming from, that's all just coming from this force displacement relationship. Once we know the displacements at each end of a particular element within a larger structure, and we know the stiffness matrix for that element, well, then we can work out what the forces are at each end of the bar, which essentially is us determining the axial force within the bar. All right then. So always keep in mind that's all stiffness and stiffness matrices are. A stiffness is a thing that relates the force to the corresponding displacement. And so in this case, generalized for a bar segment, the stiffness matrix is just relating whatever forces are applied at one end, or at each end rather, to the corresponding displacements that result from those forces. That is so critical that you can understand in your mind what it is when we're talking about a stiffness matrix, because really the entire direct stiffness method and everything that we're going to subsequently do in this course relies heavily on these stiffness matrices. So it's really important, as I say, spend the time you need to spend to get it clear in your mind what this stiffness matrix is and what it's telling you. That's a stiffness matrix, and that's how you would directly derive a stiffness matrix. What I want to do now, just very briefly before we wrap up this lecture, is to just give you a sense of where it is we're going, what it is we're going to be doing. So it all starts off, well, at the center of the picture is this stiffness matrix, right? So we'll say EA over L. Core, fundamental to everything that we're going to do in this course. We are going to go and use FE equations, okay, to derive this, right? So there's going to be some FE equations. You haven't seen them yet. So FE equations, we'll just say not seen yet. All right, those guys, they are used to derive this thing. So they can be used to derive this thing. Well, we've already derived it, you might say. So why bother, working at these FE equations? Well, because they're also used to derive more complex stiffness matrices. So I'm just kind of drawing a bit of a mind map here for you. And when we say more complex stiffness matrices, what we really mean is stiffness matrices for more complex structural elements. We'll just make the note that we've already directly derived this stiffness matrix. But where to then? Once we've worked out the FE equations, and once we've also demonstrated that they can be used to derive this bar stiffness matrix, Well, then we get into the much more exciting stuff of applying what's called the direct stiffness method. So the direct stiffness method combines the element stiffness matrices to model the whole structure. Okay, and that ultimately leads us down to let's just draw a little simple structure down here. So the payoff is coming. I know that most people watching this course would really just want to be getting to this part where we actually analyze structures, and that's coming very, very soon. Because once we have the element stiffness matrices and we work out a method or a scheme for combining those together to produce structural stiffness matrices, what you end up when you have a structure stiffness matrix is you end up with a model for your entire structure. And then you can actually model the structure and you can model its behavior. And that's ultimately where we're going. And, you know, we'll get there very, very soon. So that is the sort of mind map of what we're about to do, right? So this is where we're going next, right? We're shooting for the FE equations. We're going to derive those pretty quickly, pretty straightforward, because it's going to equip you with some really powerful tools to go on it and derive this relationship for various different structural elements. And after this section, we'll then go down and see how do I actually implement this direct stiffness method, which uses the element stiffness matrices to model the behavior of structures. So this is obviously where everyone wants to get and where we're moving to quite quickly.